What you're going to see today is going to remind you a lot of something we did last week when we did curved mirror ray diagrams. These diagrams are going to be a little bit easier, but there's going to be a lot of similarities between the two. There are, first of all, two types of curved lenses, just as there are two types of curved mirrors. We've got converging and we've got diverging. But if you think back to last week when we did mirrors, a converging mirror was a concave mirror. Well, now a converging lens is a convex lens. A diverging mirror was a convex mirror. A diverging lens is a concave lens. Sorry. It's a little bit confusing. But in the end, okay, if we remember what the shapes look like, it's not so much the convex and concave nature of it, what they look like, okay, we can visualize whether light is going to converge or diverge, whether light's going to come together or spread apart. Okay, if we do that, then that tells us whether we have a converging lens or mirror or a diverging lens or mirror. Take a look at the first one, a converging lens, a convex lens. It's like a magnifying glass, right? So you see the diagram right there is a magnifying glass. What does that do? It produces an image that is bigger and is right side up. It's not very convenient when you're trying to read through a magnifying glass if it's upside down or if it's smaller. Okay, you're trying to make something bigger. So usually we're going to see something that's larger and right side up. But if you look to the right of that, there's a diagram of Chris Hadfield. There's a drop of water floating in front of him in the International Space Station as he orbits around the Earth. The drop of water is perfectly spherical, first of all, because there's no gravity acting on it. Okay, also, it's not sinking. It's not falling to the ground, right? It's floating in front of his eye. Take a look at the center of that droplet of water. What do you see? His face is upside down, and his face is smaller. His eyes are really, really close together. So not only is he producing an image that's smaller than the object as opposed to bigger, he's producing an image that's upside down instead of right side up. So it's exactly the opposite of what we saw right here with the magnifying glass. But this droplet of water that's in front of his face is essentially a magnifying glass, right? It's a convex lens, a converging lens. Why do we get the difference? Well, it all depends upon where the object is relative to the lens. Just the same as with mirrors, it depended upon where the object was relative to the mirror. Take a look down here. What do we see? Well, first of all, we see just a bunch of rays of light going through the lens of the eye. What kind of lens is that? What kind of lens do you have in your eye? Convex. A converging lens, right? There's a problem with this lens, though. This lens is causing rays of light that are going parallel to each other to converge at this point right here in front of the retina. The retina is back here. We don't want it to converge there. We want it to converge on the retina. So what do we got to do? Well, we've got to cause these rays of light to diverge a little bit, spread apart a little bit, so that when they converge too quickly as a result of the lens in the eye, they're actually converging in the right place. So what do? We put another lens in front of it, a diverging lens in front of it. This isn't drawn very well, actually. What it should do is spread that light out. Then as it goes through the converging lens, they converge together again, but because they started out going through that converging lens in the eye a little bit further apart, they converge a little bit further back. In other words, they converge on the retina of the eye. Does that make sense? Contacts work a little bit different, right? Anybody have contacts in their eyes right now? Contacts work a little bit different. The basic optics principles are the same, but the way that we use it, the way that they function in this case is a little bit different. Okay, when you have contacts in, it's essentially changing the shape of the lens of your eye. Because they're so close to your eye, there's not the opportunity for the rays of light to spread apart and then come together after they go through the lens of your eye. Okay, they can't do that. So if we're going to put it right on the surface of your eye, we can't expect the rays of light to diverge first. What we expect is the rays of light to diverge not quite as much, or not to converge quite as much, because we've changed the shape of the lens of your eye with that contact. Yeah.
So when a person has other nearsighted or farsighted, is that an issue with the face of the retina, or is that an issue with the eye?
Usually it would be the lens. Now, I wouldn't want to say, I'm not a biologist or an optometrist, so I wouldn't want to say exactly what the issue is. But basically, it would have to do with not so much the size of the lens, because the size of the lens of your eye changes. Depends upon the muscles. When you squint, right, you see differently, right? It's because the shape of your lens has changed. So for whatever reason, the shape of your lens isn't proper. Not so much the size, but the shape of your lens isn't proper to cause the light to refract into the right place. Now, whether that's a result of muscles in your eye not functioning properly, okay, or whether that's a flaw in the lens itself, I'm not really sure what the deal is with that, but it would normally be with the lens though, as opposed to the retina. What kind of lens is this? This is convex. Okay, this is converging. Don't draw this, okay? Just follow along for a second. All rays of light that are parallel to the principal axis will converge right here. What's that point right there called? Focal point. What's this point called? We're not going to call that the center of curvature, because this lens doesn't have to be circular. We're just going to call it 2F now. It's twice the focal length. Okay, it's not related to the center of a circle or a sphere or anything like that. Just 2F. And of course, this line right here we call our principal axis. All right, we got 5 ray diagrams to draw here. Let's draw the first one. First one is when we have our object well beyond the focal length. Well beyond 2F, in fact. First ray of light from the top of the object to the center of the lens. It goes from the center of the lens down through the focal point. That's a lot like the first ray that we always drew from mirrors, parallel to the principal axis down through the focal point. But with mirrors, it reflected off of the mirror instead of went through it, like it does here. Second ray, a little bit different. Second ray goes from the top of the object down through what we call the optical center of the lens. And then it just keeps going straight through. We don't need to draw a third ray. There is a third ray that we could draw, but we don't need to because we already have 2 lines intersecting here, right here. If those 2 rays came from the top of the object, they're going to converge at the top of the image. This image would be smaller. It would be inverted. And it would be real or virtual? Real. Now, I can't think of a particular application for this where you'd want to take an object that is a certain size and produce an image of it on a screen that's smaller and upside down. Okay, there may very well be some kind of application for that out there. I just can't think of one. Nor can I think of an application for this one. First ray parallel to the principal axis down through the focal point. Second ray goes down through the optical center, converges over here on the right-hand side somewhere. Characteristics to this one should be right below 2F, by the way. Characteristics here, it's going to be same size, it's going to be inverted, and it's going to be real. We can project it onto a screen if we want. We know that because we have solid lines intersecting. The next one is where we see the applications for. In fact, this one you see literally every day. Every day you come to school, at least you see this one. We've got an object between F and 2F here. First ray goes from the top of the object, parallel to the principal axis, down through the focal point. Hey, by the way, when we draw these rays of light through the lens to the middle and then down through the focal point, is it really going like that? Really refracting like that? It's not. It doesn't enter the lens straight. When it enters the lens, it bends. And then when it leaves the lens, it bends again. The reality is the actual path would look more like this. It enters like this, bends down like this, and then goes out like this. But the net effect is the same as what we draw. It's a lot easier to draw it this way than it is to draw it the proper way, and we get the same result. So let's just go with it this way. Just understand that we get refraction every time, here and here. Every time a ray of light enters a new medium, it bends. Okay, second ray of light. This one's going to go from the top of the object down through the optical center, like this. They're going to converge somewhere on the right-hand side over here. What do we see this time? We see an image that is clearly larger. It is inverted. And it is real or virtual. Solid lines are intersecting, so this one's going to be real. We got a real image. Where have you seen this every day? Where are you seeing this right now? Adam? The projector. Right? We've got an object inside that projector, which is a little LCD panel that is between the focal point of that lens and twice the focal point of that lens. That generates an image on a screen a certain distance away that is larger, that is wait a second, that's not upside down, is it? Take a look at the projector. The projector is upside down. So if our object is upside down, then our image would be right side up. Now, we're cheating a little bit there because you can also put the projector right side up and still make it show up right side up. What we do is actually electronically manipulate the object. There's a little LCD panel that creates the object, that is the object. We can make the object right side up or upside down electronically without flipping over the projector. In fact, by default, it's upside down. So by default, when I put the projector just sitting on a table the normal way, it produces an image that's right side up. In order to mount it on a ceiling like this upside down, we actually have to change a setting to flip over the object so that the object becomes upside down in an upside down projector. Does that make sense? Bottom line is we want our object to always be upside down because we want our image to be right side up. Clearly, it's a bigger image. And it's real because it's being projected onto a screen. You're probably not going to see much in terms of application for this one either, and you'll see why in just a second. Parallel down through the focal point. Second one goes down through the optical center. Where do they converge? Where do they converge? They don't. There's not much of an application for this, I don't think, because I can't imagine a situation where you're going to try to put a lens in front of an object so that you can't see the object. Maybe if you're trying to make the object invisible, maybe it's some kind of invisibility cloak. But other than that, I don't think you'd see it much. We're going to say it's no image. No image formed. Next one, last one, you've seen this a million times before. We got an object that's close to the lens. It's inside the focal length. First ray, parallel to the principal axis, down through the focal point. Second ray, down through the optical center. Nice thing about lenses, there's only ever 2 rays to draw. We don't have to ever worry about that third ray like we did with mirrors. They don't converge on the right-hand side, so let's extend them back. When they extend them back, it's going to look something like this. Those dotted rays converge back here, producing an image that looks like this. The image is right side up. It's larger. And it is real or virtual? Virtual. Where have you seen this? Where have you seen this? Sorry? Magnifying glass, yeah. With a magnifying glass, you always put the lens in front of the object, in front of the print or whatever it is that you're trying to see, and you put it pretty close, right? You put it so that the object, the newspaper or the magazine or whatever fine print that it is you're trying to read, is closer than the focal point. You may not realize you're doing that, but that's what you're doing. Okay, at some level, okay, you move this magnifying glass around, okay, you're not seeing what you want to see. So what do? You play with it until you do see what you want to see. And when you finally find what you're trying to see, and that is a magnified image, where does it end up being? Close to it. You don't necessarily know that that's where you have to put it, but you figure that out pretty quick. Okay, it becomes close to it. And when you put it close to it, Braden, take a look at the image that you see.
It's bigger.
It's bigger.
Upright.
It's upright, it's bigger, and it's, we're looking at the lens, it's virtual, right? Take a look at this, Braden, actually, for a second. Hey, from above here, okay? Right now, okay, you see, here, let's put it on the printer. You see a bigger image, upright? Yeah, I got to see here too. Back up a little bit.
Oh, I can't see it.
Okay, okay, back here. Now look through it. A little bit blurred. Okay, should be smaller, I think.
I can't, no, it's just,
No?
it's
Okay.
just like white.
Let's go to this spot. Right here. What do you see?
Still blurred. It's bigger, but it's blurred.
If I get it at the exact right spot, which is right here, I get nothing. If I have it at the exact right spot. Where am I at? Where's the lens at when I put it right here and get nothing? I look through the lens and I see nothing through it. It's at the focal point, right? Okay, you look at a ray diagram back here. When you put the magnifying glass at the focal point, in other words, when the object is the focal distance away from the lens, you're not going to get an image. Try that with a magnifying glass, literally. Try holding it way up here. See what you see. Look through it. See what you see. Bring it closer. Bring it closer. You can see an image. And then at some point, it's gone. It was right in here. Right in here where it's gone. Okay? Try it. You see a Canada flag up on the board right now. It doesn't have to be a Canada flag. We just put that up there because it's nice and bright and clear. I'm going to put a lens. You stand at the back of the room now with a convex lens, a converging lens. Okay? I'm going to aim that converging lens at that Canada flag. Okay? Right now, as I look through there, I actually see that Canada flag through the lens. It's a smaller, inverted image that I see. But what I want you to see is not so much the image that you look at through the lens, but rather the image that you're going to see in just a second on this card. Okay, look at the card. Okay, watch the card. As I move it closer and closer and closer, we're going to find pretty soon that there is a clear, sounds like just a little baby has been born or something with the little giggles we're getting from girls. We see an inverted, smaller, real image. Now, the distance from the lens to the card, to the screen, is our image distance. Because that object is a fair distance away, the rays of light that are coming from that object that actually go through the lens are approaching parallel to each other. We're not far enough away to make them perfectly parallel, but they're getting close. That means that they're going to converge where? At the image distance, right? But the image distance will be the focal length if the lines were parallel to the principal axis. They're close. Okay, so the distance that I have right here that I've measured as my image distance will also be close to the focal length. Now what I want to do is focus on something that's even further away. Okay, focus on the condos across the street there, kitty corner to the school. Okay, that's a good, probably a couple hundred meters at least, probably closer to 300 meters away. The rays of light that are coming from those condos are not parallel to each other, but the few rays that actually make it this far and go through this lens are essentially parallel to each other. So when I aim at those condos across the street, and I move this card to the place where I see a good clear image of those condos on the card, then I should have as my image distance the focal length. Does that make sense? Because the rays are parallel. So I'm going to move it. We're going to find it's going to be pretty much in the same place, but it may be slightly different, a little bit more accurate this time because we're looking at something further away. Okay, right now, I can see that window. I can see the rocks outside. There we go. Yeah, I can see 3 people or 4 people walking. I can see a couple cars going by. Oh, there's another person. Can you guys see that? Megan, can you see that? There's somebody in a red shirt. Somebody else? Have a look if you don't believe me, guys. Just come around here and have a look, okay? Just press pause there. Remember that method, okay? In a couple of days, you're going to use that method to find the focal length of a convex lens yourself, and then you're going to use that focal length to do an activity involving the lens equation that you're going to learn about in a little while here. Let's take a look, though, at the second kind of lens, second kind of curved lens, that is. This is what we call a concave lens or a diverging lens. Concave or diverging. Our object is placed well beyond 2 times the focal length, just as it was with all of the other scenarios we've drawn for lenses and mirrors. A far-off object, but this time in front of a concave lens as opposed to a convex lens. So like looking at the condos out there across the street, but looking at it through a concave lens instead of a convex lens. What are we going to see? Well, the first ray of light is going to go from the top of the object parallel to the principal axis, as you would predict. Where's it going to go from there? I'll give you 3 options. Option number 1, down through the focal point. Who says yes? Why not? Why doesn't it go down through there? That would be a mirror. It doesn't reflect off of the lens. It goes through the lens. Okay, it reflects off of a mirror. All right, so it goes through the lens down there to a point on the other side that would be like the focal point. No? Okay, third option. Who votes for up there? You don't like that? It's too bad that some of us don't like that because that's the right one. The ray of light that goes parallel to the principal axis, it diverges away from the focal point. It's like it's going away from the focal point. Go ahead. No, it hits the lens. It actually hits the lens and bends like this, right? But hits the lens, bends, and then goes up like we see it there, up and away from the focal point. It's not only until anything, it goes like that forever. Now the second ray of light, this one's an easy one. From the top of the object down through the optical center, keeps going just like it did before. They don't intersect. So what we got to do is extend the refracted rays. This one gets extended back this way. Now, a lot of people look at this and say, hey, wait, they're intersecting now. But do we make it do we make it a real image or a virtual image? We said real images are caused by solid lines intersecting. Virtuals are caused by dotted lines intersecting. What do we got here? Well, the reality is we have actually 2 dotted lines intersecting. We just don't usually draw it that way. The first dotted line is this one, right? Goes back from the first refracted ray here. The second dotted line is the line that goes back from this refracted ray. We're extending both refracted rays. Now we clearly have 2 dotted lines intersecting, producing a smaller image, a upright image, and real or virtual? Virtual. So just a minute ago, I held that convex lens in front of the window, aimed it at the condos across the street, and we saw a good, clear, sharp, focused image that was smaller, upside down, and real. Could we do that with this concave lens? What would we see? Could we see the condos across the street if we aimed it at the condos? We could, but what would we have to do to see it? We'd have to look through the lens because it's a virtual image. Make sense? We couldn't project it onto the screen. Okay, here's what I'd like you to do right now for the next few minutes here. Draw the next 4 ray diagrams. Okay, when the object is at twice the focal length, between F and 2F, at F, and inside the focal length. And let's see what we get. See if you start noticing a pattern pretty quick here. Are we starting to notice a pattern here, everyone? What do you notice about the characteristics for all 5 of those ray diagrams? Yeah, they're the same. Now, the size of the image is going to be a little bit different. The positioning is going to be a little bit different, but the characteristics will always be the same. Let's draw the next extreme. We drew it when it was really far away from the lens. Let's draw when it's really close to the lens. First ray, parallel to the principal axis, away from the focal point, down through the optical center. Extend those back. We can extend this back if we want, but in the end, we know it's going to be 2 dotted lines that intersect. Smaller, it's going to be upright, and it's going to be virtual. Same as it was for the last diagram we drew. You can see the size of the image and the position of the image is a little bit different. but still the same characteristics. Does that make sense? Okay. We'll wrap it up there for today, and we'll pick up on the math on this tomorrow.